All right, so now we can go ahead and get started with test 2 review, and this is for Chem 1305, Introduction to Chemistry. Test number 2 is going to be over chapters 4 and 5, and so I'm hoping that everyone will get an A, and so that I can shave my head if you guys get an A, all of you. All right, so that's the deal. All right, so let's go ahead and get started. We're going to start with chapter 4 first, and then chapter 5. So chapter 4 is all about the electronic structure of the atom, and that's related to a pretty complicated subfield of chemistry called physical chemistry. And we talked about a little bit of quantum physics, but it's more related to chemistry, of course, um, and not the physics side. So we're not going to look at a lot of equations and stuff like that. So you learned about light, right? And what the nature of light is. So light, by definition, is essentially an electromagnetic radiation consisting of oscillating waves of electric and magnetic fields propagating through space, and of course, at the speed of light in vacuum. And speed of light has a symbol letter C, and the speed is 300 million meters per second. So that's 3.0 times 10 raised to the eighth power meters per second. So that's pretty fast. Again, light can travel and circumnavigate the globe in um, you know 8 to 10 times in a second. So that's how fast light is. And light is also a particle. So we know that it is a wave because it has these wave-like characteristics, but it's also a particle because it contains photons, and photons by definition are massless particles of light, or energy, I should say. So again, in this review, we're just going to look at the most important concepts, and there's a total of, I believe, 22 or 23 concepts that I want to talk about that are most likely going to be on the test. All right, the second concept here is pretty straightforward, the electromagnetic radiation spectrum. So this is basically the spectrum of light, right? Because light is an electromagnetic radiation. And I mentioned that some radiations are pretty harmful, some are harmless, right? They don't have enough energy to uh, cause damage to your cells. So this is what the spectrum looks like. I know this is um, basically summarized. So you have the gamma rays on the far right hand of the spectrum, and then you have the X-rays, UV, visible in this order. So you have IR, microwaves, and radio waves. And whenever you're looking at an EM radiation spectrum, make sure that you know which ones are high in energy and which ones are low in energy. Same thing when it comes to wavelength and also frequency. So you learned in chapter 4 that all these three things are related mathematically, all right? So those are the energy, wavelength, and frequency. So gamma rays are very energetic, all right? They have high energy, they can definitely cause damage. And so in terms of frequency and wavelength, gamma rays have very short wavelength, but very high frequency. Okay, so on the right-hand side of the electromagnetic radiation spectrum, you have the short wavelength, high frequency, high energy forms of light. Whereas on the left-hand side of the electromagnetic radiation spectrum, you have the long wavelength, low frequency, and low energy uh, forms of light. That's why radio waves, microwaves, and infrared are not, they don't have a lot of energy, and so they don't really cause any damages to your skin cells or your cells in general. But UV light coming from the sun, right, ultraviolet, they can cause cancer or skin cancer if you stay too long under the sun. So that's all you really need to know regarding the electromagnetic radiation spectrum. You just have to be aware which side of the spectrum has higher energy, shorter wavelength, higher frequency. All right, so we know that light is a wave, right? We know that light is a wave because it has characteristics of a wave. And what are these characteristics of a wave? Well, the first one is amplitude, right? It's got amplitude, wavelength, and frequency. And wavelength has this symbol called lambda, which is the Greek letter. Frequency has the Greek symbol nu, nu. And amplitude is basically tells you how intense the intense the light is, and also the brightness of that light. And so the higher the amplitude, the higher the intensity. So that's all you need to know regarding amplitude. In the lecture, we focused more on wavelength and frequency. Wavelength is typically measured in meters or in nanometers. And if you're looking at a graph as shown here, where you have a wave, the wavelength is the distance between two crests or two troughs, right? The maximum, the distance between the two maxima here, or the two minima. So the measurement is the same. So that's how you measure the length of a wave. Frequency, on the other hand, is defined as the number of cycles per second. Okay, and of course, frequency is related to wavelength. So if we have two different waves here, okay, you can see that they have different wavelengths. So wave number one here has a longer wavelength. The distance between two maxima is right over here. And then for the second wave, you can see that it has shorter wavelength, right? Again, the distance between two maxima here. In terms of frequency, which is the number of cycles per second, let's assume that this is the 1 second mark here, which is equivalent to this one. You can see that wave number two has a lot more cycles per second, right? So this is 1 cycle right here, 2, 3, and so on. Over here, you only have a few cycles per second. And so in terms of frequency, the higher the number of cycles per second, the greater the frequency. And so you can easily assume just by looking at the graph here that wave number two has a higher frequency, and the one on the left has a lower frequency. So this is how you can visualize frequency and wavelength. You can also visualize amplitude here. So amplitude is essentially the distance, or the distance from the maximum height to over here on this line. Okay, so mathematically, it's half the height of the wave. So the height goes from maximum to the minimum divided by 2. That would be the amplitude. All right, let's move on to the next concept here. Concept number 4 is regarding the visible region of the electromagnetic spectrum. Okay, electromagnetic radiation spectrum, I should say. So again, the visible region of the electromagnetic radiation spectrum is actually just a small region of the spectrum, right? So let me show you the spectrum again. So this right here, this small part, is the only part in the spectrum that's visible to us, and that's why they called it the visible region. Everything else is black and white, right? You can't see them. And so here's the visible region of the electromagnetic radiation spectrum, and you can see that we have the colors of the rainbow, right? You have red, orange, yellow, green, blue, purple, or violet. And this region, of course, has a specific wavelength and energy, as well as frequency. And so the red color usually has um, a wavelength around 700 nanometer. Again, you have different shades of red, different shades of yellow and blue. But red is typically around 700 nanometers. Orange is around 600 nanometer, yellow 580, and then green is around 550, blue 450, and then purple around 400 nanometers. All right, so by just knowing the uh, the wavelength of these colors, you can identify which color is greater in energy, which one has a higher energy. So blue and purple or violet, they're closer to the UV region of the spectrum. And you know that ultraviolet can cause sunburn, and it's higher in energy compared to infrared, right? You can see that the color red is closer to infrared. And if infrared is lower in energy than ultraviolet, then red must be lower in energy compared to violet itself, right? And so energy increases from left to right in this region, right? From red to purple. So purple has shorter wavelength. That means higher in energy, higher in frequency. Whereas red here has longer wavelength, lower frequency, and lower energy. All right, so again, long wavelength on the left-hand side, low frequency, low energy. And then on the right-hand side, we have the opposite. We have the shorter wavelength, higher frequency, and higher in energy. So that's basically the relationship between wavelength, frequency, and energy, and we can prove this mathematically, of course. So how do we prove this relationship mathematically? Well, we have to look at these equations. I mentioned that there are three formulas or equations that are important in this chapter. The first one relates frequency and wavelength. So we have the Greek letter nu here, which represents frequency. And this is equivalent to c over lambda, where c is the speed of light. And again, speed of light is 300 million meters per second. And you can see that frequency is inversely proportional to the wavelength. And so if wavelength increases, frequency decreases, and vice versa. The second important equation here is E equals Planck's constant times frequency. And this basically relates energy and frequency. So energy is capital E, and frequency is the Greek letter nu. You can see that they are directly related. So if you increase one, the other one also increases. So if you were to increase frequency, you're also increasing energy because you're multiplying frequency by Planck's constant. And Planck's constant is equivalent to this number right here, 6.626 times 10 to the negative 34th joules second. And the last important equation here relates energy and wavelength. So again, what we did here for, we basically combined the first equation and the second equation. So we substituted c over lambda here for frequency. And so now we get the third equation, which is E equals hc over lambda. Planck's constant multiplied by the speed of light divided by the wavelength. And again, the wavelengths here are in meters, not nanometers. All right, so make sure that before you plug in anything into these equations, that your wavelength has to be in meters. All right, so we just looked at the mathematical relationship between these three. So how are they exactly related? So here are the equations again. And I already mentioned that frequency is inversely proportional or inversely related to wavelength, whereas energy is directly related to the frequency. Okay, so energy is directly related to frequency, but inversely proportional to the wavelength. And so if you have, so looking at frequency and wavelength here, the higher this number is, the lower frequency is, because you're dividing the speed of light by a greater, larger number, right? So the longer the wavelength, the lower the frequency. The shorter the wavelength, the greater the frequency, because now you're dividing the speed of light by a smaller, shorter wavelength. So that would increase the frequency. So that's how frequency and wavelength are related. In terms of energy and frequency, they're directly related here. So increasing one would increase the other one as well. So the higher the frequency, the higher the energy. And finally, we have energy and wavelength here. Again, you're dividing hc by wavelength. And so the larger the wavelength is, the lower the energy. Okay, and the shorter the wavelength is, the higher the energy. So we can summarize all of these things in one single statement right over here, where it says the shorter the wavelength, the higher the frequency and energy. Okay, you can also say the longer the wavelength, the lower the frequency and energy. All right, so let's take a look at an example here, or a few examples. It says, which photon has lower frequency? So we're comparing 350 nanometers versus 650 nanometers. So just by um, knowing the relationship between wavelength and frequency, which one would you predict to have lower frequency? Can anybody answer that question? What do you guys think? Mercy thinks it's the 350 nanometers. Actually, it's the 650 nanometer because it's asking for lower frequency, right? So the longer the wavelength, the lower the frequency. So that would be the 615 nanometers. And now we can prove this mathematically. So it says calculate the energy and frequency of the two photons. So we're going to need two equations here because it's asking for energy and frequency. For energy, we can use this equation. You can use the other one as well, but you would have to figure out what the frequency is first. So we can use this since we have the wavelength given, right? So we can calculate energy, which is hc over the wavelength. We can calculate the frequency here, which is equivalent to speed of light divided by the wavelength. And again, you would have to convert the wavelengths to meters first because they're given in nanometers. So let's calculate energy and frequency first for the 350 nanometers. For energy, we have Planck's constant right over here, and you would multiply this by the speed of light, which is 3 times 10 raised to the 8th power. And you divide this by the wavelength, 350 nanometers, converted to meters. And how do we convert that? Well, all you have to do is replace the nano prefix with its numerical value, which is times 10 to the negative 9. So you're essentially multiplying 350 by 10 to the negative 9. And so that's how you quickly convert nanometers to meters. And then plug this into the calculator, and what you get is 5.7 times 10 to the negative 19 joules. So that's for energy. We can also calculate frequency here. All you have to do is divide the speed of light by 350 times 10 to the negative 9. So here's the speed of light divided by uh, the wavelength in meters, and we get 8.6 times 10 raised to the 14th power inverse second. So again, frequency, the units for frequency are inverse second or hertz. So you can use either or. So that's for 350 nanometers. How do we calculate for 650? Well, we can use the same exact equations here. When you plug that into the calculator, you'll get energy of 3.1 times 10 to the negative 19 and a frequency of 4.6 times 10 raised to the 14th power. So when you compare the frequencies here for 650 and 350, the 650 has a lower frequency than the 350 nanometers. All right, so let me know if you guys have any questions or if you want to see another example. Um, Otherwise, I can move on to the next concept. All right. So Jessica is asking, what about for wavelength? So you're probably asking, how do we calculate wavelength given the frequency or maybe given the energy? So we can definitely look at an example. So just give me a minute here. All right, so let's say we have a frequency of, let's say, 7.5 times 10 to the 15th power inverse second. And I ask you to convert this to wavelength. Convert, so I'm gonna write convert to wavelength. Convert to wavelength in nanometers. How would you do that? Well, since we have frequency right over here and you're trying to convert this to wavelength, we can use that equation for frequency and rearrange that to solve for wavelength. So the equation is frequency equals speed of light divided by wavelength. And so you can rearrange this mathematically and isolate wavelength by itself. And so all you have to do is switch frequency and wavelength in the equation. And so we have wavelength equals c over frequency. And then plug in the numbers, right? So we have the speed of light, which is 3 times 10 to the 8th power meters per second. And you're dividing this by the frequency that's given, which is 7.50 times 10 to the 15th power. And this is inverse second. All right, so we can plug this into the calculator. Let's see what we get. 3 times 10 to the 8th power divided by 7.50 times 10 to the 15th. So when you plug this into the calculator, you get 4.00 times 10 to the negative 8 meter. Okay, so this is not in nanometers, but it's in meters, but it's asking you what is the wavelength in nanometers. So now you can convert this to nanometers, and you can easily convert that by dividing this number by 10 to the negative 9. All right, so plug this into the calculator and divide this by 10 to the negative 9. And we get 40 nanometers. So that's how you convert frequency to wavelength in nanometers. So again, whenever you're plugging it into the equation, what you get is the wavelength in meters, and you can convert this to nanometers by simply dividing it by 10 to the negative 9, or by multiplying this number by 10 to the positive 9. So you can do either or. If you want to see how energy is converted to wavelength, we can look at another example as well. All right, so let's say that I have energy here. Energy is, let's say, 6.00 times 10 to the negative, let's say, negative 15 joules. How do we convert this to wavelength in nanometers? So how would you do that? Well, again, you have energy and you're looking for wavelength. So you would use that equation that contains those two variables, energy and wavelength. And there's only one that contains that equation. It's hc over the wavelength. Okay, so how do we rearrange this? Well, all you have to do again is to switch lambda and energy, and we get the equation for it, hc over energy. All right, so plug in the numbers. We know what Planck's constant is. It's 6.626 times 10 to the negative 34th joules seconds, and you multiply this by the speed of light, 3.0 times 10 to the 8th power meters per second, and you divide this by the energy that's given, which is 6.00 times 10 to the negative 15. So let's plug this into the calculator, 6.626 times 10 to the negative 34th power, multiply that by the speed of light, and divide that by 6 times 10 to the negative 15. All right, so what we get here is 3.31 times 10 to the negative 11th. And again, this is in meter, okay? And we have to convert this to nanometers. And again, based on the previous example, all you have to do is divide this number by 10 to the negative 9, or multiply it by 10 to the positive 9. Okay, so let's do this using division for just consistency. So we're going to divide this by 10 to the negative 9, and we get nanometers. Okay, so 3.31 divided by 10 to the negative 9, and that is 0.033 nanometer, 0.0331 nanometer. All right, so that's how you convert energy to wavelength, and also frequency to wavelength. All right, so the next concept here is related to Bohr's model of the atom and how that's used to explain line spectra. So you remember that Niels Bohr came up with a model for the electronic structure of the atom, where you have the nucleus at the very center, and then the nucleus is surrounded by stationary states, right? And these stationary states contain the electrons, and electrons revolve around the nucleus within the stationary states. And these stationary states are also known as orbits. So you learned in high school what these are called. They're called orbits, but technically the proper terminology here is stationary states. Okay, so these states are not moving, right? They stay in place, and so that's why they called it stationary. And these electrons within these stationary states, they can jump, right, up and down. They can go from a low energy ground state. Okay, ground state means low energy, to a higher energy, which is also known as the excited state. Okay, so they can jump up to an excited state, or they can go back down to the ground state. These electrons that go to a higher energy level, they're not very stable, right? And so they have to inevitably go back down to the lower energy level, which is the ground state. So this jumping process, this is known as a transition. Okay, so they're making a transition from the ground state or low energy level to a higher energy level, the excited state. And there are two types of transition. There's what they call an absorption, because the electrons are absorbing energy from an external source, like light, for example. And so they use this energy to jump to a higher energy level, right? If you're at a low energy, the only way that these electrons can jump or can go to a higher energy level is to absorb an external source of energy. So they call this an absorption. The other type of transition is called emission. So when these electrons at a higher energy level when they go back down to a low electron moves from a low energy to a higher energy level. Emission would be the opposite. So you have an electron moving from a high energy level, the excited state, to a lower energy level. So as I mentioned earlier, once the electron is at a higher energy level, they can't permanently stay here at a higher energy level. They have to go back down to a lower energy level, because again, a lower energy level is more stable compared to a higher energy. And so that's where this next concept is. We have what they call the emission, which is when an electron goes back down to a lower energy level. And so when they do, energy has to be released or emitted, and that's why they call this an emission, in the form of light or heat. Okay, so it depends on where the electron uh, transitioned from and to. Okay, so if the energy is high, then most likely it's going to be in the form of light. But if the energy is low, most likely it's going to be in a form of heat. All right, so this light, of course, contains photons, and photons contain a specific energy depending on what the wavelength is, right? Again, by definition, a photon is a massless packet of energy, with a specific wavelength. And so this combination of different wavelengths make up what they call the spectral lines. And so a lot of elements in the periodic table, they can absorb and emit energy. And so depending on what the combination is, you'll be able to identify what kind of element you have. Okay, because again, the spectral line or the emission line spectrum is unique to each element in the periodic table. You can look up emission spectroscopy or atomic spectroscopy, and this technique is used in uh, a lot of research. Okay, so you can use it for determining what kind of elements you have in a given sample. So if you want to know what metals you have in your drinking water, you can use atomic emission spectroscopy or atomic spectroscopy in general. All right, so now we're getting into concept number 8, which is quantum mechanical model. So this concept is just a definition of what quantum mechanical model is. Um, it's summarized in this definition. So it basically explains the behavior of the electrons. Um, like for example, electrons behaving like light or particle, I should say, or a wave. So that's what it means by behavior of electrons. How they exist in atoms and where they exist in atoms, and how they determine physical and chemical properties. So that's what the quantum mechanical model basically answers. So electrons can actually also behave like light, meaning that they have this wave particle duality. Electrons and light, they behave the same way. They can behave as a wave or as a particle. And so they call this the wave particle duality. What that means is, again, as I mentioned, these electrons and light, they possess particle-like and wave-like characteristics. So you know that they have wave-like characteristics if they have amplitude, wavelength, and frequency. You know that electrons are subatomic particles, and so they have particle-like characteristics as well. Light also has particle-like characteristics because of the fact that they contain photons, which are particles of light. All right, so now we're getting into energy levels, sublevels, orbitals, and electrons. So this part right here is a huge part of the quantum mechanical model. Again, it explains the electronic structure of an atom. Okay, we know that atoms have energy levels, and atoms have all these things, of course. So when you look at, let's say, the Bohr's model of the atom, where you have the nucleus in the middle, and then you have these stationary states or orbits in the quantum mechanical model, they're no longer called stationary states, right? They're now called energy levels. And energy levels have the symbol lowercase n. So you can have energy level 1, energy level 2, 3, 4, 5, 6, and so on and so forth. And you learned that the higher the n value, the higher the energy. So as you go farther away from the nucleus, the electrons gain more energy. Okay, so electrons in the fourth energy level would have a higher energy than electrons in energy levels 3, 2, or 1. Atoms also have energy sublevels. So these are energy levels within the energy, or these are energy sublevels within the energy levels. And there's a lot of different types. You learn S, P, D, and F sublevels. And the number of sublevels per energy level will depend on what the energy level is. So energy level N has N number of sublevels. So if you have energy level 1, then you have 1 energy level. If you have energy level 3, then that contains 3 energy sublevels. It matches the energy level. All right. Namely, these sublevels are the 3s, 3p, and the 3d for n equals 3. If you have n equals 4, then you have 4 sublevels, and that would be the 4s, 4p, 4d, and 4f for a total of 4 sublevels. And then within these sublevels, you have the orbitals. And orbitals, by definition, are regions of space where there's a high probability of finding an electron. So this is basically where electrons live. This is where they reside. Okay, so there are a certain number of orbitals per sublevel. So depending on what sublevel you have, you can have 1, 3, 5, or 7 orbitals. So in an s sublevel, for example, you only have 1 orbital, and that's the s orbital. If you have p sublevel, there are 3 different p orbitals. In a d sublevel, there's a total of 5 different d orbitals. And in an f sublevel, contains 7 different f orbitals. Okay, so it's essentially the first 4 odd numbers here, 1, 3, 5, 7. And again, that's S, P, D, F in that order. All right, so you'll also encounter somewhere on the test, one of the test questions um, regarding this concept, calculating the maximum number of electrons per given orbital, sublevel, or energy level. So let's say, for example, for energy level 1, what is the maximum number of electrons that you can have in the first energy level? So I gave you guys an equation for, I guess, for the energy level. It's 2n squared. So all you have to do is plug the value into that equation, 2n squared. So for example, for the first energy level, that would be 1 squared times 2, which is equivalent to 2. So the maximum number of electrons for that the first energy level can accommodate is 2. All right, and then for the second energy level, plug this into the equation. 2 times 2 is 4, multiply that by 2 is 8. So for the second energy level, a total of 8 electrons. For the third energy level, that would be 3 times 3 is 6, multiply that by 2. I'm sorry, 3 times 3 is 9, multiply that by 2, you get 18. So 18 electrons maximum. For the energy sublevel, it will depend on what sublevel you have. Right, so these are the energy sublevels. You have S sublevel, P, D, and F sublevel. So the S sublevel can only hold a maximum of 2 electrons. Okay, the P sublevel can hold a maximum of 6 electrons, the D sublevel 10, and the F sublevel 14. So essentially it increases by 4. Right, so 2 plus 4 is 6, 6 plus 4 is 10, 10 plus 4 is 14. And the next sublevels here, we have the G, the H, I, and so on, the next letters of the alphabet, basically. All right, and the number of orbitals, or max number of electrons per orbital, it will depend on the orbitals. Well, not really, but the maximum number of electrons per orbital is the same regardless of what the orbital is. So it's 2 electrons for any one orbital. So if you have one s orbital, that can hold a maximum of 2 electrons. If you have a p orbital, 2 electrons. Same thing with D or F. All right, so don't get the orbitals and sublevels confused. All right, and so we're almost halfway here. The next concept is regarding orbital shapes. Um, again, orbitals are regions of space where there's a high probability of finding an electron. And again, they are mathematical representations, right? And so you can graph them mathematically, three-dimensionally. So for example, an s orbital is spherical in shape, right? So if you have a 1s orbital, it would be spherical. A 2s orbital is an s orbital in a higher energy level, which is 2, which would be larger in energy and also larger in size. A 3s orbital would be even larger with higher energy. P orbitals are they have dumbbell shape. So they have 2 lobes. We have 3 different orientations of the p orbital. You have a p sub x, p sub y, and p sub z. And that's why you have a total of 3 different p orbitals. And a p sub y would essentially look like the first one, p sub x, except the lobes here uh, lie on the y-axis. And you can guess what a pz look like. The lobes lie on the z-axis. All right, and the d orbitals, there are 5 different orientations, 5 different ones. So you have a dx, dxy, dxz, dyz, dx squared minus y squared, and dz squared. And the first 3 here, they look exactly alike. It's just how they are oriented in space. For example, the dxy, you have the lobes in between the x and y axes. Okay, the dxz looks exactly like the first one, except the lobes lie between the x and the z axes. Same thing for the dyz, except the lobes lie on the yz plane. And the x squared minus y squared, the lobes lie on the x and y axes. And finally, this dz squared looks like double pacifier where you have 2 lobes lie on the z-axis and then a ring surrounding uh, the middle of the node here, basically the node. All right, so make sure that you know the different shapes of the orbitals. We didn't cover the f orbitals because those are a little bit more challenging. All right, and the next topic here is going to be regarding electron configurations. So electron configurations basically show you where the electrons reside, which orbitals, which energy levels, and so on and so forth. So whenever you're writing out the electron configurations for any elements, this is your best friend right here, right? So this is the orbital diagram, or I'm sorry, a diagram that you can use to help you decide where the electrons go, right? So you go from the lowest energy level and you work your way up. So again, that's called the Aufbau principle, where you fill the orbitals with electrons from the lowest energy level to the highest energy level. So it goes in this direction. So you have the 1s followed by the 2s, and then the 2p, 3s, 3p, 4s, so on and so forth. Okay, so you can use this diagram to guide you whenever you're writing out the electron configurations. All right, so when you're following these arrows here, you fill out the 1s first, followed by the 2s, and then you have the 2p and the 3s, and then the 3p, and then the 4s, and then the 3d, 4p, 5s, and then 4d, 5p, 6s, and so on and so forth. All right, so again, you have to take into account the maximum number of electrons that can occupy each sublevel. So if you have an S sublevel, that would be 2 electrons max, P sublevel 6 maximum, D sublevel 10 electrons max, and then the F sublevel 14 electrons max. So let's take a look at 3 examples here. We have potassium, calcium, and scandium. When you look at the periodic table and identify how many electrons you have for potassium, there's a total of 19 electrons. And so you have to distribute all 19 electrons by writing out the electron configuration. So we have um, the 1s, 2s, 2p, all the way to 4s. And then we're going to distribute all 19 electrons. So that would be 2 in the 1s, 2 in the 2s, 6 in the 2p, 2 in 3s, 6 in the 3p, and then 1 in the 4s. And when you count all these superscripts, these numbers up top, that should equate to 19 electrons. So that's how you distribute all 19 electrons. We can do the same thing for calcium. Calcium is the next element after potassium, so it has 20 electrons. And so the electron configuration would look just like the potassium's, except you have one extra electron that goes in the 4s. So that would be 4s2 instead of 4s1. And so again, when you add up all the numbers, all the superscripts, that should add up to 20 electrons. Scandium is the next element after calcium, which is a transition element, and it has a total of 21 electrons. So distributing all 21 electrons would look something like this, where the 21st electron would be in the 3d sublevel. So you would have a 3d1. So you fill all these sublevels up to 4s2 and then 3d1. All right, and that's how you write out electron configurations for any elements in the periodic table. There's also the noble gas electron configurations. So we have the normal electron configurations here for potassium, calcium, and scandium. Noble gas is essentially a shortcut, so you don't have to keep writing all these, this first part here. So whenever you're writing the noble gas electron configuration, your starting point is always the noble gas, the preceding noble gas. So for potassium, calcium, and scandium, they all have the same uh, noble gas, right? The preceding noble gas is the same, which is argon. Okay, so that's going to be your starting point, and argon has 18 electrons. So you would essentially replace these 18 electrons here from 1s all the way to 3p with argon, and then write out the rest. So that would be argon in brackets, followed by the remaining electron configuration, which is 4s1. We can do the same thing for calcium. Again, argon in brackets, and then 4s2. And for scandium, that would be argon again, followed by 4s2 and 3d1. And that's how you write out noble gas electron configurations. All right, and concept number 19 or 13 are the orbital diagrams. Again, these are um, another version of electron configurations, except you're using boxes that represent orbitals. or lines that represent the orbitals. So again, we're going to take a look at the same examples here. We have potassium, calcium, and scandium. And all you have to do is come up with boxes or lines that represent these orbitals, right? So 1s sublevel contains one orbital. The 2p sublevel contains three orbitals, 1, 2, and 3. Same thing for the 3p. It has three lines here, 1, 2, and 3. All right, so all you have to do now is fill them up with electrons, which are represented by half-headed arrows. All right, so for the first one, you would put two electrons, one that's pointing up and the other one is pointing down according to Hund's rule. All right, and then the 2s, you have two electrons, so that would be up and down. For the 2p, you would put electrons in each orbital first, singly, and then start pairing them up. So here's the first one, and then start pairing them up. And then the 3s, you can see that there are two electrons here, so two electrons will go in the 3s. 3p6, so 6 electrons total here, and then one in the 4s. So this is the orbital diagram for potassium. And you can do the same thing for calcium and scandium. Looks something like this for calcium, where the 4s contains two electrons. And then for scandium, you have the 4s and the 3d. The 3d sublevel contains a total of 5 orbitals. Right, so you would have 4 boxes of 4 lines here with only one electron, so that would go in the first one by convention. All right, the next topic here is regarding valence electrons and how they're different from core electrons. So again, the valence electrons are the outermost electrons, and these electrons are the ones that are involved in chemical bonding. They are on the surface, essentially, of the atoms. And the number of valence electrons for a given element essentially matches that element's group number. So if the element is in group 1a, then it contains one valence electron. Group 2a, two valence electrons, 3a, three valence electrons, and so on and so forth. The core electrons, on the other hand, are the electrons other than the valence electrons, right? The rest of the electrons other than the valence. And they are not involved in chemical bonding. They're buried deep within the atom, and so they're very difficult to access. It would require a huge amount of energy to even touch these core electrons. So how do we determine the number of valence electrons and core electrons for a given element? So let's take a look at these three examples here. We have sodium, magnesium, and aluminum. So you would look in the periodic table for sodium, and you can see that sodium is in group 1a, and so it would have one valence electron. The total number of electrons for sodium is 11. Okay, magnesium 12, aluminum 13, based on the atomic number. All right, and then for the number of valence electrons, 1 for sodium because it's in group 1, 2 for magnesium because it's in group 2, and 3 for aluminum because it's in group 3. To determine the number of core electrons, all you have to do is subtract the number of valence electrons from its total. And so 11 minus 1 is 10. So the number of core electrons would be the same for all three, sodium, magnesium, and aluminum.